folks that decide these things years ago, they knew something moved in those wires, right? They didn't know whether it was the positives or the negatives. Somebody had a guess. I think it was Ben Franklin. He said the positives move. So we call the flow, the current, the direction of current, the direction of positive charge movement. If positive charge is moved, that's the direction of the current. Okay? Years later, I'm not sure how many, but a few years later, they figured out that it wasn't the positives that move, it's the negatives, the electrons actually move. But we already had developed this way of thinking that current is the direction of positive charge movement. And instead of just cutting our losses and changing it at that instant, they stuck with it. Now we're even more, it's like us with not switching to the metric system, right? We should have just done it 50 years ago. Now it's harder and harder to change. So anyway, we're stuck with this. We draw the arrow for current. The direction of positive charges would flow if positive charges flowed. But it's really the negative charges flowing in the opposite direction. So this simulator is showing the negatives. It shows the electrons moving in the circuit. We would typically draw the arrow pointing in the other direction for current. The arrow comes out of the long side, out of the positive side of the battery. So I would draw it this way. I would draw current going that way in my circuit. But it's really the negatives going the opposite direction. Okay? Good question. All right, so what I'll do, I'm going to hand out a sheet for you. And it's got a little more complicated circuit on it. And you can work on it at home. Check it with your PhET simulator. Okay, see if you get the right answer. And I wanted to try to hit one more thing today. We've got resistors in series and parallel, but we know about another type of device, don't we? A capacitor. And capacitors can also be hooked up in circuits in various ways, in series and in parallel. So we have to be careful here because these are capacitors and this is my battery. Some books, they draw the battery instead of with two lines like that. Instead of drawing a battery like this, they draw it like a double like that so it doesn't get confused as easily with the capacitor. Those are both ways of drawing batteries. All right, so if we have a series configuration of capacitors or a parallel configuration, what do you think is going to happen? Let's look at the parallel configuration first. We know something about capacitors. A parallel plate capacitor, how does the capacitance depend on the surface area of those plates? Right, because capacitance tells us how much charge it can store with the given voltage difference, with the given battery. And the bigger those plates, the easier it is to push charges in there with the same battery. So what happens when we put another capacitor right next to it and tie the plates together? It seems like it's as if we just increase the surface area of the plate. We did, basically. So we take the surface area here. Now all of a sudden we tie it to another capacitor. We tie it to another one. It's like we've just increased the surface area. We've increased the capacitance. The same battery can now store charge not just on C1, but also on C2 and C3. So the capacitance goes up. We just add them up, just like we're adding area together to the plates of those capacitors, hooking the areas up together. So C equivalent, C1 plus C2 plus C3, as many as we have in parallel. This is the tricky part. In series, the capacitance actually goes down. And this is why. When we hook up the battery here, an electron moves. An electron moves from the left plate of C1 to the right plate of C3. Right? An electron moves over there, leaves a positive behind. Remember, we draw a capacitor with this gap between those plates. There's a gap in there. There's no electrical connection. Charges cannot flow from the left plate of C1 to the right plate of C1. Right? There's a dielectric, an insulator in there. So when you hook this battery up, one way to think of it, a positive charge goes around here, but really what's happening, the electron goes around to the other side, and it leaves a positive behind. And it moves a few more. Now what happens internally? You get an electron buildup on the right plate of C3, so that attracts, right? Well, actually what it does, it repels some of the electrons from the left plate of C3, right? They get repelled. They move as far away as they can, leaving some positives behind. And over here we attract some electrons, and they come all the way over to the right plate of C1, leaving some positives behind over here. But all of this stuff that's just a rearrangement internally. You can't get that back out. The total charge stored in this arrangement is just what's on the left plate of C1 and the right plate of C3. Everything internal there, you can't get that back out. If you hook this up to a flash on a camera, that internal charge is just going to go back to where it was initially. It's not going to go through the flash of the camera. So you're losing something here. You're not getting out everything that's stored. So you end up with this. You end up with 1 over the equivalent capacitance, 1 over C1, plus 1 over C2, plus 1 over C3. And the total charge stored, if this is Q, and this is minus Q, and this is plus Q, and minus Q, and plus Q, and minus Q, the total charge stored is just Q. It's not 3Q. And all three of those capacitors have the same charge stored. It doesn't matter what the capacitances are. C1, C2, C3, they might all be different, but they're all going to have the same Q, the same charge stored in them. And the total charge stored in the system is equal to that Q, what's in each one of those. Because all the internal isn't really stored. It's just a rearrangement that goes back to the way it was when you removed the battery. Okay? So it's just the opposite. We'll talk about this more next time, but it's just the opposite of resistors. Remember, resistors in series had this formula, and resistors in parallel had the other formula. Capacitors, it's the opposite. But you want to think a little bit about why it is. Why is it that way? Okay? Resistors, remember, think about going through the check stand at your supermarket. Excuse me. Or walking down a hallway with doors, taking out a key, unlocking the door, getting through it, things like that. Capacitors, you have to think about these charges moving around, and that when you put them in parallel, you're just making one bigger capacitor. And when you put them in series, what happens is you're breaking up the voltage over each one of those, and you're not getting any extra charge out for those middle ones. So you can see why the overall capacitance, the overall charge stored, goes down when you hook them up in series. Question?
You have an even number of capacitors in there? Because it's easy to visualize the separation when you have 3 there, but you put 4, it seems like it might be a weird effect in the middle. You know what I mean?
Yeah, question is, does it matter whether it's even number or odd number? It doesn't matter. What happens is there's no electrical connection in between. So I could have had another one in here, C2, C3, C4. I could have had 2 in here. But these charges are moving between the leftmost plate and the rightmost plate, and everything in the middle is just redistributing because of the electrostatic attraction and repulsion with those outer 2 plates. Okay? Stop here, pick it up next time with, so you've got the techniques now to do series and parallel resistors, series and parallel capacitors, and Kirchhoff's rules for more complicated circuits. And that should get you through most of this chapter.